will be a little bit of a review from what Mike talked about yesterday and from Daryl talked about as far as some of the basics of FRP. But then I'll get into some more detail about the actual C581 testing that we do, how we manufacture the coupons, and then I'll go through a variety of case histories just to show you some FRP, service life, different types of service conditions. Some of the expectations, again, we'll go over some of the vocabulary of FRP, the testing criteria that we use in order to determine whether or not a resin is suitable for an environment, and then go through those test results and those case histories. Starting with FRP and some of the places that it's used in a variety of plants. You can see it in storage tanks, cooling towers, as well as the tank wagons, variety of process vessels, and then in many plant facilities, it's used a lot in the wastewater treatment of whatever the end products are. This is an example of a mineral processing facility where you have a lot of FRP used in the leaching process, where you have a lot of strong acids and solvents. Again, storage tanks, slurry environments, storage of acids, and also the treatment of the wastewater near the end of the process. As we discussed yesterday, when you combine good engineering, good design, good fabrication, FRP is a very durable product for a variety of applications. These are just a variety of examples where you've got some excellent service life. Here you've got 43 years of service, several that are in the upper 20s. So again, when you are able to fabricate a well done vessel, it's going to last a very long time. This is the same slide that Mike showed you, just showing you that not only selecting the proper materials, resins, promoters, initiators, as well as good proper part design, and then a good reputable fabrication. All those work together to provide a excellent vessel that's going to provide a long service life. Again, a review of some of the vocabulary that Daryl touched on, FRP or GRP, fiber or glass reinforced polymer or glass reinforced plastic, you'll see both of those. The corrosion barrier or the chemical resistant liner, I think by now we know that's the innermost liner that's exposed to the corrosive environment, consisting of a veil layer with a high resin content backed by a couple plies of the chopped strand mat. And then chopped strand mat is that fiber that's used not only in the corrosion barrier, but then also in the structural barrier, which is going to be that load-bearing part of the equipment with a varying thickness, just depending on the required engineering for that part. So over here, just a brief summary of some of the different types of epoxy vinyl ester resins that you will commonly see. What we call the Dewatering 411 series is a bisphenol A vinyl ester resin. It's going to have excellent temperature resistance and overall good resistance to acids and bases. And then your Dewatering 470 series is a Novolac epoxy vinyl ester. That will also see excellent resistance to acids, not so recommended in caustic environments, but also excellent solvent resistance and temperature resistance. And then for the applications where you need that good corrosion resistance as well as flame retardancy, the Dewatering 510 series, which is a brominated vinyl ester resin. So essentially, in making these, they're reacted with a methacrylic acid, and then styrene is the monomer that produces these resins. In the middle is just an example of the different veil types that we've talked about. Carbon veil, polyester or nexus veil, and then also sea glass veil. Again, these are going to provide that primary layer of resistance on the innermost part of the vessel, and depending on your environment, will give you the determination as to which type of veil that you would want to use. Over here is a more detailed diagram of the laminate, starting with the innermost liner, your veil layer. As we talked about, that's a high resin content, usually about 90%, and then backed by 2 layers of the chopped strand mat. Together, that forms your primary corrosion barrier. Generally, it's going to be about 100 mils thick. Some environments require something thicker, maybe a chlorine environment or high concentrations of hydrochloric acid. And then behind that, your structural portion, which can consist of alternating layers of chopped strand mat and woven roving, filament winding, unidirectional, just depends on the engineering requirements for that vessel. So together, again, proper material selection, veil selection is going to allow you to produce an excellent vessel with a long service life. So now we'll go more into the specifics of the ASTM C581 testing and how we use those results to make a resin recommendation. When we do laboratory testing per the ASTM C581, gives us a good starting point for determining which resin is going to be suitable for which environment. But then an even better option is if we can either submerge pipe sections or coupons, give those to the customer, they can put them in the actual environment at their facility, and then after a period of time, whether it's 6 months, a year, they can send those samples back to us, and we can evaluate those in the laboratory and determine whether or not that resin is good for that specific environment. So that's an even better way of determining what resins are suitable. And then case histories are actually going to be the best predictor. If we've got a tank that's in a certain environment and we're able to follow that with regular inspections over a course of many years, we can use that to predict success in future environments. So all 3 of those ways combined gives us a really good idea of what resin is going to be suitable in what environment. This is just a picture of what we would do in the laboratory to make the coupons. We've got the chopped strand mat and the veil, and then your resin, and then here, just showing you how we would roll out the laminate using the stops to make a very even thickness throughout. And I actually brought a couple samples of the coupons that we would actually make. You can just pass those around. Just gives you an idea of what we can make and then supply to you if you need them to put in your environment. Again, just a diagram of a coupon where this is going to be a little bit different than your corrosion liner in a vessel because you actually have veil on both sides. So when you immerse that coupon in the testing environment, it's actually going to be a little bit more severe because you're going to have attack on both sides of the coupon, whereas if you've got a vessel in service, you're only going to have attack on one side. But it's a good representation of how that resin is going to perform in that environment. And then here's just an actual tank cutout, just a good comparison of how thin your corrosion barrier really is compared to the structural part of your laminate. Yet this barrier is your critical part in providing that corrosion resistance. This is a picture of what it would actually look like in the laboratory where we would test the coupons. We are able to immerse them in various chemicals. We can control the temperature and test them at elevated temperatures when necessary. And what we would normally do is immerse the coupons and then pull out a coupon at 1 month, 3 months, 6 months, and then 12 months. And at each of those intervals, we would visually evaluate the coupon for wicking, surface, color, blistering, any type of change that we see in that coupon, we would record. Generally, we rate that on a scale of 1 to 5. And then we would also submit those for fluxual testing and measure the retention over that period of time. So what we like to see at 12 months is very little change in the surface of the coupon, and then also at least a 50% retention for those flex properties. That gives us a good indication that that material is going to perform well in that environment. This is just a picture of many coupons that have been exposed to different environments. Just gives you an idea of the different types of attack we see. Sometimes the coupon has a very minimal change, whereas some of these, depending on the environment, they really change a lot. Again, an example of an unexposed coupon, and then one that we would evaluate where we would see some wicking. You use a backlight to just be able to see how that coupon has been attacked in that environment. Now I'll go through an actual study that we did and how we gathered that data and then use that to make different recommendations. So in this study, again, we did it according to the ASTM C581 standard. We tested 9 to 15% sodium hypochlorite, temperatures between 120 and 150 degrees Fahrenheit, and then did the visual and physical property evaluations at 1, 3, 6, and 12 months. We looked at 3 different types of vinyl ester resins, the bisphenol A, the no black epoxy vinyl ester, and then also the brominated epoxy vinyl ester resin. Looked at the 3 veil types, sea glass veil, polyester veil, and carbon veil. And then for this, we also evaluated 2 cure systems, an MEKP cobalt system, and then also the BPO DMA cure system. In the first study, we used sea glass veil for all of the coupons and then evaluated the 3 different resins, the bisphenol A, the no black epoxy, and then the brominated. All the same cure system, and then an evaluation looking at the surface appearance. There was essentially no gloss left on the epoxy, no black epoxy vinyl ester. The bisphenol A was slightly flat, but then the Dewatering 510, the brominated vinyl ester, still had a very glossy appearance and really no signs of resin attack. So that was a good indication that the Dewatering 510B, or the brominated resin, performed best in the sodium hypochlorite environment. What we saw with the 411 or the bisphenol A, it was also suitable at the lower concentrations, but overall the 510 would provide you with the best resistance.
Excuse me, was that in that solution, was that mixture turning, or is it just a steady state?
Normally it's just, it's not being agitated, but it is checked and changed to make sure that it maintains that certain concentration, because it will decompose over time weekly, yeah. So to maintain the concentration that we started with. In this one, it was evaluated at 10% sodium hypochlorite at 150 degrees Fahrenheit, and here we evaluated the veil types. We used the polyester and the sea glass and the carbon veil, all with the brominated epoxy vinyl ester. Same cure system throughout, BPO DMA. And if you look at the flex strength retention values, as I mentioned, we want to see over 50%. And in this one, using the sea glass veil, we had essentially over 50% on all those retentions with very slight resin attack. Whereas with the polyester veil, we did see lower retention values and slightly more resin attack. With the carbon veil, essentially it was no veil left after 1 month. So based on this study, sea glass veil is going to provide the best resistance at the lower concentrations of hypochlorite and at the temperatures around 150. In this study, we evaluated the bisphenol A vinyl ester resin and looked at the cure system. We used a BPO DMA cure system, and over, this is time and weight change, there was very little weight change in the coupon after the 10 months, whereas when we used a cobalt MEKP cure system, especially when we used a higher level of cobalt, you saw a more dramatic drop off in the weight change. A little bit lower percent cobalt was not as substantial of a difference. So overall, when you're using a sodium hypochlorite solution, you want to recommend a BPO-DMA cure system, at least in the corrosion barrier, because what actually can happen is the presence of metals or cobalt in this situation can promote the formation of hypochlorous acid, which is going to be aggressive to the FRP. So when possible, you want to use a BPO-DMA cure system, or at least a low cobalt system, just to get the best performance. Looking at the cure system and a veil comparison, again using the brominated vinyl ester resin. The sea glass veil provided slightly better results than the polyester veil. Very comparable retentions, but a little bit better surface appearance and no resin attack. So overall, again, your brominated vinyl ester resin with a BPO-DMA cure system and the sea glass veil provides your best resistance and best performance in sodium hypochlorite. So this just summarizes what we just went through, with the recommended resin being a Dewatering 510 series, again the brominated. The Dewatering 411, or the standard bisphenol A, is suitable for the lower temperatures and the lower concentrations of sodium hypochlorite. Your recommended veil, generally 2 layers of sea glass. And then the cure system, as I talked about, the BPO-DMA is going to be the optimum system and recommended for that corrosion liner. Cobalt MEKP can be used in the structural portion just because that's not going to be directly exposed to the sodium hypochlorite. This is a case study where we actually were able to send the coupons to a customer. They immersed them in 25% sodium hypochlorite at their facility, and then after 7 years, we were able to get those coupons back and then do a visual inspection and also some flex testing. And again, as I mentioned in the beginning, this is going to provide you with a little bit more detailed data because you're actually immersing them in a process. So they were removed in January of 2021 after 7 years of exposure. And we did see, as you can see, some cracking. And as Mike mentioned earlier yesterday, this cracking was really only on the surface, and it was determined that it was due to thermal cycling, where they were introducing cold sodium hypochlorite into a warmer tank. So we did see this cracking, but it did not affect the integrity of the resin. And once it formed, it didn't progress over the years, and it was really only in that veil layer. Really, most of them, there was very little chemical attack or change in the surface of the coupons. Some were slightly duller than others. Essentially, with the 510, there was very little cracking with the synthetic veil. And as I mentioned, the cracking, we were able to determine by looking at the cross section that was really due to some thermal cycling as opposed to any chemical attack. Looking at a summary of the flex properties, over here is the flex strength, and these values were a little bit lower just because of the cracking that was present in the veil layer. And then overall, all of the coupons had very good flex modulus retention after those 7 years. Now I'll move into some various case histories and just applications of the different resins in different types of chemicals. Here we have a hydrochloric acid storage tank operating at about 100 degrees Fahrenheit. This was a Dewatering 470 tank that was installed in 1971, and then it was actually replaced in 1998 after 27 years of service. And even at this point, there was very minor chemical attack, and there had been no maintenance required over those 27 years. This is a liner for a stack. The service conditions consisted of wet gases with ammonium bisulfate and some traces of sulfur dioxide. In this case, it was originally a brick stack that was installed in 1922, and then in 1973 they went in and actually lined it with the brominated vinyl ester resin. And as of 1996, when it was inspected, it was still in good condition after 23 years of service. This is a sodium hypochlorite storage tank fabricated with a brominated epoxy vinyl ester. It was storing sodium hypochlorite at ambient temperature, and it was installed at a wastewater treatment plant. Corrosion liner here consisted of one layer of sea glass veil backed up by one layer of synthetic veil. Again, the BPA DMA cure system was used for that primary corrosion barrier, and then an MEKP cobalt cure system was used for those structural layers. This is a petrochemical facility in Saudi Arabia, and just an example of a large facility with multiple applications for FRP. A little bit interesting, it's located right near the Arabian Gulf, which happens to be one of the saltiest bodies of water in the world. So not only do you have the interior of the vessels needing to be chemical resistant, but you've got that very salty, briny environment. So FRP is very suitable here because it provides you with some external resistance as well as the internal corrosion resistance. This is a sodium hydroxide storage tank. Excellent opportunity for Dewatering 411. That's probably the best resin to use for caustic environments. Corrosion liner. This is an example where synthetic veil is going to be your veil of choice as opposed to your sea glass veil. This tank was installed in 1993 and still continues in service with no maintenance required as of 25 years. This is a picture of some dewatering lines in a power plant. An example of, we talked about yesterday about abrasion resistance. So in this situation, some abrasion resistance was needed, so 40% aluminum oxide was incorporated into that corrosion liner to provide that necessary abrasion resistance in this service. So these were installed in 2005. This is a large odor control system using the brominated epoxy vinyl ester resin. This facility installation took place in 2010 at a sanitation district in California, and it was treating hydrogen sulfide and other types of organic compounds at the wastewater facility. Ambient temperature, your standard 100 mil corrosion liner. So just an example of the size of some of these pieces of equipment. This is a chlorine cooling tower, an excellent application for the Dewatering 470 Novolac epoxy vinyl ester. Very low pH and about 24 years of service. These are some large tanks at a mining facility. These tanks were actually field fabricated. We talked about that in various presentations over the last couple of days. So that's an advantage, again, of FRP. It can be fabricated in your shop, but if you've got very large tanks where transportation may be an issue, they can be fabricated on site. These are some large power plant tanks, and again, some field winding. Again, you can do that at the end user site and avoid that costly transportation of large FRP vessels. This is firewater piping, and in this case, out on some of these platforms, you're going to need that fire retardant. So this is an excellent application for the Dewatering 510 brominated vinyl ester, which provides you that resistance to the salt water, as well as the resistance to the salty air and the fire retardants that's needed. This is an application, again, out on a platform, but it is the cable tray. So if you see up here, we're supporting all the cables. Again, an excellent application for FRP because you have the resistance as well as that flame retardance that's required on a lot of these platforms. This is a lined steel tank that was handling raw oil at temperatures up around 160 degrees Fahrenheit. It was lined with a Dewatering vinyl ester in about 1995, and then it was inspected in 2013 after about 18 years of service, and there was some minor deterioration that was detected around some of the steel supports, so they were able to go in and repair those areas and then reapply a top coat and then return that tank to service. So I know we've talked a lot about, how you can repair and FRP that's in service, so this is a good example of where they did have to go in and do some minor repair but didn't have to actually replace the tank. This is some FRP piping that was handling crude oil and water at about 100 degrees Fahrenheit. Again, in an offshore platform, excellent application for the Dewatering epoxy vinyl ester. This highlights how FRP is lighter weight, so the installation is a little bit easier, and at the time of this installation, it was estimated that there was a 50% cost savings over using steel, just because of the decrease in the weight and the ability to install this. Just go through a few conclusions before we finish up. So I went through how we gather all this data, and we summarize it in what we call our resin selection guide. And it has essentially 1,000 or more chemical environments that we've tested or we've had case histories on. And this is just an example, has the resins listed across the top, and then what temperature each of these resins would be suitable to. Now, a lot of times we'll have customers that may have a mixture of chemicals, so you can certainly contact us, we can work through it, or if possible, sending coupons to you and immersing those in your environment, that again is an excellent way to determine whether or not that resin is going to be suitable for your specific application. And if you can certainly contact us at dewatering@ineos.com, and again, we can walk you through your application and help work you through and get the best material selection for you. Again, epoxy vinyl esters provide excellent temperature resistance, excellent chemical resistance in a wide variety of industries. They've been used throughout pulp and paper industry, wastewater treatment, chlorine, so a lot of places where there is FRP. We do have case histories to support this data. So it allows us to really provide you with the full picture of how that FRP is going to work in your system. So again, feel free to contact us for recommendations or questions, information. We have a lot of data on our resins that we can share with you if you've got specific requirements. But that's really what we're here for, Mike and I. So if you've got questions, feel free to contact us anytime. So, are there any questions?
For the pure systems, you mentioned the cobalt versus the DNA. Besides chemical resistance, are there other differences why you pick one over the other, like price or ease of use?
Ease of use, most people will pick the cobalt MEKP system. Again, there are certain environments, sodium hypochlorite being one of them, where BPO-DMA does show some performance advantages. But generally speaking, when possible, customers, fabricators will use cobalt MEKP.
I don't think C581 talks about the environment, but because of the long durations, have you noticed anything like the the first lights or anything impacting the coupons? Do you try to, if there's any impact, or do you shelter them at all from lights?
From lights?
Yeah, because of long durations, I know it's minor.
Yeah, we don't normally shelter them from light, but like I said, as far as the stability of whatever we have them in, we do check that regularly to make sure that it's staying at the concentration that we want it to be. But we've not seen a big detriment with exposure to light.
Yeah, typically UV attack on the FRP is just on the exterior. It only goes a few mils deep. We've got case histories and examples where it looks pretty ugly on the outside, where you start getting fiber bloom, the surface fibers start showing, but it doesn't affect the structural properties. It's only a cosmetic issue.
Do you have any data on the effect of permeation on the structural layers of RP, those layers that are not directly exposed to the chemicals but are affected by permeation?
We do have studies that we've done in different environments where we have done physical property testing to just really determine how that affects the structural. That would be a good situation where if you contacted us, we could, look through what we have and provide you with, physical property data, visual evaluation of how that affects both the corrosion barrier and then the structural portion.
Some chlorine products are not good with RP, especially insect fluorescent acid. Do you have any information that someone come up with, with resin or solid glass that can resist these kind of chemicals?
You said fluoride-containing compounds?
Yes.
FRP is actually going to be resistant to those using the synthetic veil. What we've found is certainly you don't want to use the sea glass veil because the fluoride does attack the sea glass veil. But with synthetic veil and say in hydrochloric acid, generally your Dewatering 470 with a synthetic veil will provide you with a good service life.
Up to a certain concentration, which is in our guide, what the concentration is. There is a maximum concentration that we recommend to use. I think it's about 30% concentration is the maximum concentration for hydrochloric acid.
Concentration and temperature important.
Yeah, that all makes, plays into the recommendation on that one.
What's the lifetime for that FRP?
If it's ambient temperature and 20 to 30% concentration, you're probably going to get 15, 20 years.
And I didn't, in our selection guide, which is either online or you can get a hard copy, we do list the concentrations over here. So as Mike said, in HF, that's probably going to go up to only about 30%.
Good.
You did mention the external corrosion benefits in a salt environment for FRP. Is there a specific resin that you would recommend that's different from structural that you may be using? Or I guess there's something specific that you use for that?
Your standard bisphenol A vinyl ester like the Dewatering 411 would really provide you with the corrosion resistance that you would need. Has excellent resistance in salt, seawater, saltwater environments.
Yeah, actually, saltwater is actually not very aggressive toward FRP. Even some polyesters can even handle saltwater. It's actually less aggressive than pure water. So the more salt, the better.
And we've talked about that a little bit before, for the exterior corrosion barriers. There's a UV inhibitor to basically protect against basically radiant light hitting it. And we also have, there's a wax additive that basically seals it out and kind of gives you that harder surface on top, usually we're putting at least extra veil on the outside, sometimes a matte in the veil. I think it's going to be a little bit more severe service. But the resins don't change. We just add those additives and we can take care of that.
say here that, when you think of fiberglass and some of the things we struggle in some of our Lubrizol sites where they think of fiberglass as being something just off the shelf, like you just go grab it and you just throw it in, it works in any application and does all these wonderful things, and it can do those things, right? But it's always a matter of understanding what the heck it is, right? What the resin, the cures.
All those other components.
But also, I mean, you don't think about it, but just like you'd asked about UV, right? Making sure you have the right resistance for UV. If you need grounding for the offshore markets and things like that, you have to ground it. You can put grounding in if you need it. If you don't need it, they won't. You know, but just understanding those little things that you may not even think about, or with metals, it's just, they all do it, right? But you need them, because if you don't do them up front, right,
It's called-
it's really difficult to
It's
come
hard-
back
It's
later.
harder to do it after the fact.
And it's way more costly later. And the worst thing we could ever do is we get something in there and then it doesn't work. And not only doesn't work, but we can't really fix it. And you take it out and put something else in. And management, the further up you go, the less they're gonna know about all these, you know, I don't care about the rest. It works or it doesn't work. And why didn't it work? And so just again, spending that time up front, consulting with the right people to understand what you need and take some of those situations under, even though they may seem obvious, but you still need to put them out there to make sure they're covered. So I don't think it can be a great material.
Sorry to cover this, but does your chemical resistance tables include the catalyst systems that's recommended with the resin?
If there's an application like for sodium hypochlorite, we would have a footnote that would say BPO DMA cure system recommended. If it's your standard chlorine, that won't be indicated every time. So if there's an exception, yes, you'd have, you know, the veil, there might be a footnote stating 2 layers of sea glass veil, or BPO DMA cure recommended for the corrosion barrier, MEKP for the structural portion. So those exceptions are generally, I think there's about 24 different footnotes. So those will indicate when there's an exception really to the rule.
So you gotta pay attention.
Any more questions for Lisa? All right, well, thank you, Lisa.